Folks, I'm going to wait another 5 minutes as people zoom into the class.
Okay, let's get started. Today we're going to be talking about conditional statements. And when we see a statement in the form of if some condition, then some conclusion, or if some hypothesis, then some conclusion, that type of statement is called conditional because the truth of the statement, in other words, Q, is conditioned by the truth of the statement P. And we denote the condition as P, therefore Q. Okay, so Jacob's not able to dial in at this time. Well, I am recording, so he can watch the recording. Okay, so again, we have a statement of the form if P, then Q, denoted by P with an arrow pointing to Q. P is the hypothesis and Q is the conclusion. So again, the notation for the conditional statement is an arrow. Arrow is a connective, and that makes it like the and or the or connectives, and it joins two statements together to create a new statement. And of course, that statement is P, then Q. So to define P, then Q as a statement, we have to specify the truth values for P, then Q, as we specified the truth values for P and Q and P or Q. And of course, we go with the everyday meanings for these statements to get their truth values. Here comes Jacob now. Okay, so here's the truth table for the P, then Q. So if P, then Q, if P is true and Q is true, then P, then Q is true. If P is true and Q is false, then P, then Q is false. And if P is false in both cases, then the statement P, then Q is true. So that's the case where we have a false hypothesis and a true statement is known as vacuously true or true by default. So if we look at a statement like, if you show up for work Monday morning, then you'll get the job, is vacuously true if you don't show up for work on Monday morning. So in general, when the if part of an if-then statement is false, the statement as a whole is said to be true, regardless of whether the conclusion is true or false. So we have our statements here. If 0 equals 1, then 1 equals 2. So as strange as this may seem, since the hypothesis of this statement is false, the statement as a whole is true. So in expressions that have the arrow operator, there's going to be precedence. And the precedence is that and or statements are performed before an arrow a statement or a then if then statement, and a negation is performed before an or an or statement. And when we have and ors included in the same statement, then we can use parentheses to indicate the order of occurrence. Okay, so let's take a minute and do the truth table for P or not Q, therefore not P. Yes. The dash P is the same as the tilde P. Okay, let's take a look at this one. So again, we construct a truth table. We begin with the variables representing our statements. We have P and Q in this case. So we have 4 combinations of possible truth values: true, 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 false, false, true, and false, false. Then just for our convenience, we're going to take the negation of P and the negation of Q. So we get false, 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 true, true, false, and true, true. Then we're going to do a P or not Q. So in the first one, P is true, so that makes this statement true. Second one, P is true, so it makes the statement true. Third one, P is false and not Q is false, so that makes this false. And in the fourth one, P is false and not Q is true, so that makes our P or not Q that true in that case. Then what we want to do next is look at the conditional. If P or not Q, then not P. So let's get the true statements from this. In this case, P or Q is true, and not P over here is false. So when you have a condition, if the premise is true and the conclusion is false, then the statement is false. Then next we have the case where P or not Q is true, and then we look at therefore P. Again, that's false. So again, we have a case where the condition is true and the conclusion is false, so the statement as a whole is false. Next, we come down, P or not Q is false, and that's going to make this statement true regardless of what not P is. Just so happens not P was true, but this is going to make that a true statement. And then finally, we have P or not Q is true, and then not P is true. So that makes it true. So that's the truth table for that particular compound statement. Okay, any questions on that one? All right. So let's go on to look at logical equivalences using the conditional operator. So here we've got a situation where we have division into cases. We want to show that P or Q, therefore R, is equivalent to P, therefore R, and Q, therefore R. And this is known as a division into cases in terms of logic. I may have someone else. Yeah, someone else is coming in to the class. Okay. So take a minute and then we'll go over that. Actually, this is a fairly lengthy truth table to set up. So take about 5 minutes and work through it yourself, and then we'll go over the answer. Okay, let's take a look at this. So of course, we're going to create a truth table to establish the logical equivalence. And what we have to show is that in the truth table, this statement, P or Q, therefore R, has the same truth values as P, then R, and Q, then R. So we start off, in this case, we have 3 variables. And of course, they each have 2 possibilities, true or false. So 2 cubed is 8. We have 8 possible combinations. True, 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 false, true, false, true, true, false, 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 true, true, false, true, false, 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 true, and then false, false, false. And as a convenience, we'll start to create truth tables for some of the building blocks for the target statements. So we'll have P or Q. So in the case where P and Q are both true, we get a true. Again, P and Q are both true, we get a true. P is true, Q is false, we get a true. Same thing again, P is true, Q is false, we get a true. Here, P is false and Q is true, we get a true. P is false and Q is true, again, we get a true. And then both are false, we get a false, and again, both are false, we get a false. Next, we'll build the conditional if P then R. So if P here is P is true, R is true, that's going to be a true statement. If P is true and R is false, then as a whole, P then R is false. In this case, P is true and R is true, P then R is true. Then we get P is true, R is false. Then as a whole, the statement is false. And then in the last 4 cases, P is false. So in that case, the statement as a whole is vacuously true. So we have true, 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 true. Then the next convenience building block is if Q, then R. So we have true and true gives us a true. True, false gives us a false. False, true gives us a true. False and false gives us a true. True, true gives us a true. True, false gives us a false. And then the last 2 cases, Q is false. So the statement as a whole is vacuously true. So now we've got our building blocks. Let's do the truth table for the first compound statement, which is P or Q, therefore R. So we've got P or Q here is true, R is true. Therefore, the statement is true. P or Q is true, R is false. Statement as a whole is false. P and Q are true, R is true, statement's true. P or Q is true and R is false. So that means the statement as a whole is false. P or Q is true and R is true, statement's true. P or Q is true, R is false, so the statement is false. And then in the last 2 cases, P or Q is false, so that the overall statement, the overall conditional is vacuously true. So that's the first thing. Now we want to compare it with this division into cases, where we break that down into P, then R, and Q, then R. So if they are logically equivalent, they'll have the same truth tables. So let's look at P, then R, and Q, then R. So true, true, the and becomes true. False, false gives us a false with the and. True, true gives us a true with the and. False, true gives us a false with the and. True, true gives us a true with the and. True, false gives us a false. And then true, true, and true, true gives us two truths at the end. So if we compare these two statements, they have the same truth table, so they are logically equivalent. Okay, any questions on that one? Again, this is something in logic that's done quite often, is this division into cases. Okay, so let's see how we can represent the if-then construct as an equivalent, logically equivalent OR construct. So here we have an OR construct, and we want to establish the logical equivalence between not P or Q and P, if P, then Q. So spend a moment and go over that one. Let's take this statement. We are going to rewrite the following statement in an if-then form. So not P or Q is equivalent to P, therefore Q. And we could show that with a truth table, but we're asked here to look at this statement, rewrite the following statement, which has an OR, and rewrite it so that it is in if-then form. So spend a moment and look over that one. Okay, let's take a look at this one. So if we let the variable not P stand for you get to work on time, and Q, you are fired, then not P or Q is going to be the statement you get to work on time or you are fired. Then again, not P is you get to work on time, so P is you do not get to work on time. So P then Q, if P then Q is going to be if you do not get to work on time, then you are fired. And we can see intuitively that they are equivalent statements. Okay, let's look at the negation of a conditional statement. So the negation of if then P is logically equivalent to P and not Q. And so we can denote it like this. Negation of if P then Q is logically equivalent to P and not Q. So now we're asked to write some negations for each of the following statements. If my car is in the repair shop, then I cannot get to class. And if Sarah lives in Athens, then she lives in Greece. So go ahead and write the negations of each of those statements. Okay, let's take a look at these. So we want to write a negation for the statement, if my car is in the repair shop, then I can't get to class. And we remember from the previous slide that the negation of an if statement is, so in other words, the negation of if P then Q is going to be P is true and Q and not Q is true. So to negate that, the first if statement, if my car is in the repair shop and I cannot get to class, the negation of that is that my car is in the repair shop and I can get to class. Likewise, the negation of the second one is if Sarah lives in Athens, then she lives in Greece. We have the statement, Sarah lives in Athens and she does not live in Greece. So not Q, P, P. So, for example, Sarah might live in Athens, Georgia, or Athens, Ohio, or Athens, Wisconsin. And so she lives in Athens, but not in Greece. When you say other statements, what other statements? Oh, you got them? Okay. Yes, okay. Okay, very good. Okay, let's look at the contrapositive of a conditional statement. And there's an equivalence between a conditional statement and its contrapositive. So the contrapositive of if P then Q is if not Q, then not P. Symbolically, we're saying that if P then Q is logically equivalent to if not Q, then not P. So a conditional statement is logically equivalent to its contrapositive. Okay, let's take a minute and go over these two statements and write the contrapositives of each of them. So the first one, if Howard can swim across the lake, then Howard can swim to the island. And then the second one is if today is Easter, then tomorrow is Monday. Yes, the PowerPoint is on Blackboard. It's under the course materials. Okay, let's take a look at these. And then there's a couple questions on our course website, and I'll show that to everyone after we go over these two problems. And let me before we do that, I'm just going to get on to UMBC. Okay, so let's take a look at our course website. And a couple of questions came up about the location of the various materials like the PowerPoint and the videos. So if we go to our course website, Computer Science 203 Discrete Structures, there's a folder known as Course Materials. So click on that. And you have the Zoom meeting invite that you can always go to get to our Zoom meetings. There's a folder called Lectures. And in that folder, you'll find all the PowerPoints. You can just, obviously today we're on lecture 5. And then the videos are under a folder called Videos. So I have 3 videos up there. Today I'll have a 4th one as well. Now to find out the schedule for what we're doing, you can go to Syllabus, and there's a file called Schedule. So you can pull that up and just go to the date that you're interested in, and it'll tell you what we're covering on that particular day. So today, of course, is the 9th, and so we're covering conditional statements. Okay, so any questions on where the lecture slides are and where the videos are? Okay, very good. And yeah, we will go over the homeworks in class, after everybody's turned them in. Hopefully we'll do that on Thursday. Okay, let's now go back to this problem, the contrapositives of these two statements. Let's do the contrapositives. So we've got if Howard can swim across the lake, then Howard can swim to the island. The contrapositive is the negative of each of these statements. So if Howard cannot swim to the island, then he cannot swim across the lake. And then likewise for the second statement, if today is Easter, then tomorrow is Monday. So we take the negatives or the negations of both of those. If tomorrow is not Monday, then today is not Easter. Okay, any questions on the contrapositives? Okay, let's go on and we'll look at converse and inverse of conditional statements. So first, it's important to note that the contrapositive is logically equivalent to the conditional statement it's derived from. However, the converse and the inverse of a conditional statement are not logically equivalent. So if we have a statement in the form of if P, then Q, the converse is if Q, then P, and the inverse is if not P, then not Q. Again, these are not logically equivalent statements. Okay, let's practice doing some converse and inverse statements. Take a moment and write the both the converse and the inverse for these two statements. If Howard can swim across the lake, then Howard can swim to the island. And B, if today is Easter, then tomorrow is Monday. Okay, let's take a look at the converse and inverse of these statements. So the first statement was, if Howard can swim across the lake, then Howard can swim to the island. The converse of that statement is, if Howard can swim to the island, then Howard can swim across the lake. The inverse of that statement is, if Howard cannot swim across the lake, then he cannot swim to the island. And then the second statement is, if today is Easter, then tomorrow is Monday. And so the converse of that is, if tomorrow is Monday, then today is Easter. And the inverse is, if today is not Easter, then tomorrow is not Monday. And again, the converse and the inverse are not logically equivalent to the conditional statement. Okay, any questions on writing a, well, again, the inverse is not the same as the contrapositive. If we look at the inverse, it's going to be a statement in the form not P, therefore not Q. And the contrapositive is going to be not Q, then P. You want me to put the screen back on? Okay. Okay, go ahead and take a picture if you want. I mean, okay, so I'm assuming you got it. Okay, you're welcome. Okay, so a conditional statement and its converse are not logically equivalent. A conditional statement and its inverse are not logically equivalent. But the converse and the inverse of a conditional statement are logically equivalent to each other. Okay, let's take a look at only if and the biconditional, which is if and only if. So to say P only if Q is to say that if P occurs, then Q must also occur. And that's because of the logical equivalence of a statement and its contrapositive. So P only if Q means if not Q, then not P. But of course, the contrapositive of that is if P, then Q. So P only if Q is logically equivalent to if P, then Q. Okay, let's take a minute and rewrite an only if statement into if then. So let's take this statement and rewrite it into an if then statement. So this has only if in it, and we want to make this a if then statement. Okay, let's take a look at this one. So again, we want to convert this statement that has an only if. John will break the world's record for the mile run only if he runs the mile in less than 4 minutes. So we can replace it with just the standard if then. We keep the same P and Q. If John breaks the world record, then he runs the mile in under 4 minutes. Okay, and now let's take a look at the biconditional. That's the case where it's P is true if and only if Q is true. And so we have the vacuously true statement where they're both false. The whole statement ends up being true. And then we have, if they're both true, you get a true. If one of them is false, you get a false. If they're both false, then you've got a vacuously true statement, and it ends up as the statement as a whole becomes true. So again, the order of precedence is going to be that if and only if has the same precedence as if then. And of course, they're performed after all of the ands and ors are performed. And the ands and the ors are performed only after all the negations are performed. And of course, we can use parentheses to indicate the order of operations as well. So here's the equivalent of the if and only if in a truth table. So we take P and Q, and we've got 4 different combinations of true false. And we do if P then Q, true, false, true, true. For Q then P is going to be true, vacuously true, false, and then vacuously true. And of course, we have our truth table for if P, if and only if Q. That's just by definition, true, false, false, true. And we can show that that's equivalent to if P then Q and if Q then P. So we take if P then Q and if Q then P, true, true, we get a true, false, true, we get a false, true, false, we get a false, and then true, true, we get a true. So this shows that we have a logical equivalence between if and only if, and if P then Q, and if Q then P. Okay, and let's take a minute and rewrite this as 2 if-then statements. Okay, let's take a look at this one. So we have the if and only if statement. This computer program is correct if and only if it produces correct answers. So we can change the if and only if into two if-then statements joined with an and. So if the program's correct, then it produces correct answers. And if it produces correct answers, then the program is correct. Okay. Okay, let me switch back. You can go ahead and take your picture. Okay. All right. Okay, and let's finish up by looking at necessary and sufficient conditions. So if we say that R is a sufficient condition for S, that means if R, then S. If we say R is a necessary condition for S, then we're saying if not R, then not S. And then, of course, if R is a necessary condition for S, that also means if S, then R. And so if R is a necessary and sufficient condition for S, that means R if and only if S. And then let's finish up. Just take this statement. So if John is eligible to vote, then he is at least 18 years old. So the truth of the condition that John is eligible to vote is sufficient to ensure the truth condition that John is at least 18 years old. And the condition that John is at least 18 years old is necessary for the condition John is eligible to vote is true. Okay, so we're at the end of the class. It ends at 11:15, so almost perfect timing. Any questions on what we've covered here today? Okay, see you on Thursday. Okay, bye.